Transformers have revolutionized the field of machine learning, powering breakthroughs in natural language processing, computer vision, and beyond. This beginner-friendly course guides you step by step through the advancements that make transformers more accurate, efficient, and scalable than ever before. As these models continue to shape the future of AI, understanding their inner workings and recent innovations is essential for anyone looking to stay relevant in the rapidly evolving tech landscape. Imad Saddik developed this course.
Hi everyone, I hope you are all doing good. This is a follow-up course to the previous one that I have created and shared here on FreeCodeCamp, where I talked about how to train your first large language model. In that course, we have used the transformer architecture that was introduced in the 2017 paper, Attention is All You Need. Now, 8 years have passed and the transformer architecture has evolved quite a bit. This is why I created this course in order to basically learn about these methods that were created in the past few years. We are going to learn about different positional encodings, different attention mechanisms, and how to tweak few things in order to improve the efficiency and performance of the transformer architecture. If you are curious about what we are going to achieve at the end of this course without watching it till the end, here is a quick summary. The curve you see on top refers to the baseline model, which is basically the transformer model that we created in the previous course that was using the 2017 architecture. And now, after applying the different methods that you are going to learn in this course, such as multi-head latent attention, layer norm, post-normalization, and no dropout, you can see that the loss starts decreasing. So from the previous model that we created previously, we were able to reduce the loss by 11%, which is a lot. And this proves that, yes, these ideas that researchers have proposed, they work and they help reduce the memory usage. You will see that in some cases we reduced the memory usage by 50%. In my case, I have a RTX 4070. Previously, the 2017 model was using roughly 7 gigabytes of VRAM while training. But now, thanks to multi-head latent attention, the model uses only 3.5 gigabytes of VRAM, which helps a lot in maybe increasing the batch size. Also, the inference speed has increased by a lot. Previously, I was getting just 100 tokens per second. Now I can get 400 plus tokens per second, which is really great. And we'll see other things in this course. So I hope you are excited about this one. Now let's get started.
Hi everyone. After I uploaded my course on how to train LLMs, I got some really great feedback. Thank you so much. As you can see from this slide, this course is titled The Transformer Journey from 2017 to 2025. This is the introductory video, and let me explain why I wanted to create this course. In the previous course, Train Your Own Language Model, I have used techniques from the 2017 paper, Attention is All You Need. Since then, researchers have made a lot of improvements to the transformer architecture. So, in this new course, which is a continuation of the first one, I will show you some of these newer techniques and we will compare them to the original ones to see if they actually make a difference. At the end of the course, I will create two models, one using the 2017 architecture and another one using the latest improvements. Then we will compare their results, especially the loss curves, and see if the newer model really performs better. In the upcoming video, I will try to compare the methods that are used to encode the position. In the first course, I have used absolute positional encoding, but there are other methods such as relative positional encoding or rotary positional encodings. So we are going to see all of these methods and compare them to see which one performs the best. See you in the next video. Hi everyone! In this video, we will compare different ways to tell a transformer model where each word appears in a sentence. This is called positional encoding. Why do we need positional encoding at all? Let's look at an example. Imagine we take this sentence and break it into individual tokens like this and turn each token into an embedding. Here is the embedding vector for the word hi. Without positional encoding, the same vector is used no matter where hi appears in the sentence. That's a problem because the self-attention layer needs to understand word order. That's why we need to add positional information. But how we do that? There are a few ways to add positional information. The main types are absolute positional encoding and relative positional encoding. Let's go back to our example. We have the embedding tensor and the positional encoding tensor. We simply add them before sending them to the self-attention layer. So how do we actually build this positional encoding tensor? This is what we are going to see in this video. Let's start with absolute positional encoding. There are two main types. The first one is learnable positional encoding. In this method, we add a special tensor of weights, which is going to be learned during training, one for each position. So here is the matrix, or here are the weights that are going to be added to the transformer model. And as you can see here, we have positions, and this can handle up to block size. So during training, we are going to learn each position individually. And here you can see that we have the embedding size. So this is the shape of the matrix. The shape is the max length, which is block size, by embedding size. During training, the model learns what values work best for each position. At the end, we get a tensor, let's call it WF, which means the final weights, that contains all the positional vectors. But this method has a key limitation. It does not generalize to longer sequences than what it was trained on. And in this case, it's block size. So if you decide to use sentences that are longer than block size, this method will not work. Another issue is that each position is learned independently. So the model does not know that position 5 comes before position 20 because there is no relationship between them. If you shuffle the tokens in the input sequence, the model won't notice anything is wrong. That's a weakness of this approach. Next, we have sinusoidal positional encoding. Instead of learning position vectors, we use mathematical formulas, sine and cosine waves, with different frequencies. As you can see, here are the formulas we use to generate them. This method was used in the original transformer paper. Because it is formula-based, we don't need to learn anything, and we can handle inputs longer than what the model saw during training. Because we have just two formulas and we can just pass the values and we will get the positional encoding for that specific position. Here is how this method works. We build a tensor shaped max length by embedding size, like what we have seen before. And here, let's just focus on the 20th position. We apply the formulas that I have showed you in the previous slide for each dimension of the embedding. Here is what the wave plot looks like. The x-axis is the position, and the y-axis is the embedding dimension. At position 20, we sample values from all the waves, And just like that, we create our positional vector. If you want to get the vector at position, let's say 60, you come here, you intersect these waves and you get the values. And just like that, you construct the positional vector at that specific position. That's it for absolute methods. Let's move on to relative positional encoding. Instead of focusing on where each token is in the sentence, this method cares about how far apart tokens are from each other. This method does not modify the embedding itself. Instead, it changes how self-attention works by including information about the distance between tokens. For example, if we are attending from the token high, for example, if we are attending from the word high, the token Imad might be one step away and the token Najma 3 steps away. And this number basically means the distance between the token high and the other token. You can see that the distance between high and high is 0 because it's the same token, but the other ones that come after have positive distance. But in the other case, let's take the second high. You can see that this one will have a distance of 0, but the ones that come before it will have a negative distance, and the ones that come after it will have a positive distance. What's cool is that nearby words or tokens have more influence and distant ones have less influence, just like how natural language works. So this is how relative positional encoding works, and it's, as you saw, it's different from absolute positional encoding. Now let's talk about rotary positional embedding. This method combines the best of both worlds. It captures both absolute and relative positions. It does this by rotating token embeddings in space. Imagine our embedding space is two-dimensional. Let's say that the token Imad is located here. Now we add a token before it. Let's say that we added high. Now rope, this method, will rotate the token Imad by a fixed angle, theta, for each new token added before it. So if the token Imad is the second token in the sequence, rope will rotate it by one angle. If it is, in this case, located at the fifth position, so 1, 2, 3, 4, 5, rope will rotate it by 4 theta. And theta is just the rotation angle. So yeah, this is how this method works. And also, what's amazing about rope is that it preserves the relative angle between tokens. Let's look at this sentence. My friend is Imad. The angle between the tokens friend and Imad is represented here, represents their relationship. So let's say that we changed that sentence to this one. Who is your friend? My friend is Imad. You can see that because here we added tokens before this sentence, we need to rotate these tokens. And as you can see, the angle between them is preserved. And just like that, rope preserves relative positions even if the sentence structure changes. Here are some great resources I used to learn these different positional encoding methods. You have Jake's blog on relative positional encoding, this YouTube channel that explains rotary positional encoding. I highly recommend this video. It is really great. Christopher's Hugging Face blog on positional encoding, and my own GitHub repository. Here I try to keep updating the resources file with the new links that I find useful. Here it is if you are wondering about it. So just click on the resources and you'll find the useful resources there. Now that we have seen all the methods, let's test them. I will train a small model using the Atlas set dataset, and to save time, I will only train for one epoch for each method. So here are the methods that we are going to test. So we are going to test positional encoding, absolute, relative, sinusoidal, and rotary positional encoding. After each run, I will save the training and validation losses so we can compare them. Let's start with no positional encoding. This one is easy. Let me show you the diagram. We just remove the positional encoding layer from our transformer. So you can see that here is the sentence that we convert into individual tokens. We get the embedding, so the word embedding, and then before we used to compute the positional encoding and add the two tensors. In this method, we are going to remove this part from the transformer architecture and do the training. So you can see that here I say that don't add positional encoding to the embedding tensor. So this should be removed. Let's look at the code in VS Code. In the previous course, we used this script, model.py, to create our GPT class, or this one, so GPT language model. I have just copied this script and created a new one that I called model no positional encoding. And let me show you the difference. This one it's not that hard to understand. So here you can see that before we had two embedding tables, one for the token embedding and the other one for position embedding. In the forward pass, you can see that we take the input. So here are the input tokens that we got from the input sequence. We pass that to the token embedding and positional embedding. After that, to get the input that will go into the blocks, we take the token embedding and add to it the positional embedding. Now, look here in model no positional encoding, you can see that I have removed the positional embedding table. And in the forward pass, I take the input tokens, I pass that to the embedding table, and I create my input. So you can see that this is the only change. Just remove the positional embedding and take the token embedding and consider that as the input. Okay, so after doing this, I have created a notebook to test this. So it's this one, no positional encoding. And again, this notebook, I just took one of the previous notebooks in the previous course that I used to do pre-training. And this is the only change. So instead of importing the GPT language model class from model, I am importing it from this new script. And also I have made sure to tweak these parameters so that I get a small model, because I will be doing a lot of experiments and I don't want this to take me a lot of time. So I want to test this on a small model just to confirm that these methods work. And then once you will see in the end of this video, once we get the method that works well, then we are going to increase the size of the model and use it. But this time, because we are just doing a lot of experiments, we want to do it on a small model. I have also changed one thing, which is the evaluation method. So here we have this estimate loss method that we call periodically during the training loop. But before, in the previous course, I used to take random batches for evaluation. This time I have changed this method to use the same batch each time, so we can track improvement clearly. And this is how I have done that. So you can see that here I have this. So we have evaluation batches, which is set to 1000 batch. You can change this value if you like. The more, the better. Here I have get evaluation indices, and this one works both for training and validation. And here you can see that I compute this only once and then I reuse it. So evaluation indices, this dictionary will contain the batches for training and validation. And here you can see that we are getting them randomly, but only once. But later, when I call estimate loss and use the get batch for loss estimation, you can see that here I am using evaluation indices and I am providing those indices to the get batch for loss estimation. This allows me to get the same batches during evaluation, and it will show us if the model is improving during training or not. Also, let's go down. So here is the training loop. Here I have also added a learning rate scheduler. I have used cosine annealing learning rate. with warm-up. So why we use cosine, not just cosine, but why do we use learning rate schedulers in general? Basically, during training, we set the learning rate to a fixed value, let's say 1e minus 4. And that value will be used during training. It will not change. Learning rate schedulers allow you to change that value dynamically based on the number of epochs or the number of iterations. So here we are using cosine annealing learning rate scheduler with warm-up. What does it mean? So here you can see that we are computing the warm-up iterations. Now warm-up will take the learning rate and keep increasing it until we reach this number of iterations. And later it will start decreasing. Here is an image that I found that explains it. So you can see that this is the warm-up phase. The learning rate starts from a minimum value and goes to a maximum value. Then it starts decreasing following a cosine wave. And this is exactly what we have in the code. So we have the warm-up iterations, which is the first phase of this scheduler. And after the warm-up phase, we are going to use this scheduler to decay the learning rate and until it reaches this minimum learning rate value. So yeah, this is something that I have added to the training loop. And yeah, these are the only changes that I have made, and everything stayed the same. So after training, I have already done the training, and I have saved the training and validation losses. And now let's go back to the slides to show you what we got. I am back, and here is the plot. So you can see that here we have two curves. So we have the training loss and validation loss. And here I have used no positional encoding. And as you can see, the loss was going down, but then it stagnated, which means that the model is underfitting. And this is probably because the model is small. But we don't care about this. We want to compare the methods. So this is the first one. We have the graphs. Now we are going to go to and before that, I just want to mention the training time. So for one epoch, the model took roughly 2 hours to train. The next method is absolute positional encoding. And we are going to focus on the learnable version. This is the one we used in the previous course, so no code changes are needed. You saw in VS Code that we have a script called model.py, and we are going to use that one. So I will not go to VS Code, I will directly show you the results and compare this method to the no positional encoding. So here we have two graphs, one for the training loss and the other one for the validation loss. The orange line is absolute positional encoding and the blue line is the no positional encoding method. And as you can see in both graphs, the absolute positional encoding method performs better than no positional encoding. And this was expected because, as I said, adding more information to the transformer helps it to learn better. And again, the training time, so this method also took roughly 2 hours and 10 minutes. So there is no difference in training time. I am keeping track of the training time because this is something that we need to take into consideration, because if we get two methods that work, that give us the same performance, but one takes more time to train, then this will help us choose which method to keep. Now we are looking at sinusoidal positional encoding. This is another way to add positional information to tokens. This method is pretty interesting. On paper, it should perform just as well as the learnable version, but it does not have any learnable parameters. So if it performs like the previous method, which is absolute positional encoding with learnable parameters, this will be good because it will save us parameters. Let's see how this one is implemented in code. Okay, so I will remove this, script, and I have another one which is called model sinusoidal positional encoding. I will put it here, and let me scroll until I find the GPT language model class. So as you can see, we don't have the embedding table for positions. So this means that we remove those parameters from the model. But here I have added positional encoding. So this method will compute the positional encoding up to block size. And let me go back to that method. Also, I need some space. Okay, great. So you can see that here, create sinusoidal encoding will use the two formulas that I have showed you in the slides. It will use the sine function and cos function to compute the positional encodings. And this, the implementation that I have here, basically will just use those functions. So yeah, as you can see here, we have that 10,000 value that I have showed you in the slides. And yeah, we are going to, the sine wave is used for the even positions, and the cosine value is used for the odd positions. And at the end, we will get a positional encoding tensor of shape 1 by max length by embedding size. And we compute these values only once. So when we instantiate a new instance of the GPT language model class inside the constructor, we are going to call that method and store them and store those positional encodings in this buffer that we called positional encoding, and later we are just going to use them. So this is the difference between sinusoidal positional encoding and absolute positional encoding with learned parameters. Here we have 0 parameters that we add, but we compute the values beforehand so that we use them later. Okay, so here is the sinusoidal encoding. And now where do we use them? So you can see that here in the forward pass, again, we did the same thing. So we take the input tokens, we pass them through the embedding table. This gives us the token embedding. And here I try to add the shapes because when creating a model, this is the most important thing to look at. So the shapes are very important. And after that, we get the positional encoding. And remember, where do we get this? Because we have that stored in this buffer, we have access to this variable or to this tensor. And here we need to take just a slice. If we have a sequence that has just 10 tokens, we are going to take just the first 10 values from this tensor, or the first 10 vectors from the tensor. We don't want to go up to block size. So we get the positional encoding and we add that to the token embedding tensor to get the inputs that will go to the next layers in the transformer. After that, I have done the same thing. I have this notebook improving the transformer sinusoidal positional encoding. Inside, I have done the same thing. I have made the model small, so the size is just 11 million parameters. I have made sure to change the way we evaluate the model, and I have added the learning rate scheduler. And I have run this, I have saved the training and validation losses, and I have created the graph to compare the 3 methods. So let's go to the slides and let's see if this one performed well or not. Here are the graphs, and again we are comparing the sinusoidal positional encoding to the other ones in both training and validation. Surprisingly, this method performed worse than both other methods on both training and validation. So you can see that in some cases, so here the gap is a little bit small between sinusoidal and no positional encoding, but during training the gap is a little bit bigger. So this means that using learnable parameters is better than just pre-computing those with the sine and cosine formulas that we have seen. Okay, let's move on. Before that, I always forget to mention the training time. Also, this one took 2 hours and 10 minutes. Next up, we have relative positional encoding. There are a few versions of this method, but I will show you the one with learnable parameters. Here is the idea. We define a range of relative distances with this parameter max relative distance. Let's say if this parameter is set to 8, we will have two distances. We will have negative distances and positive distances. This is what we have seen before. Because the tokens that come before the token will have negative distances, and the ones that have positive distances, or the ones that come after the token, will have positive distances. And that range is called a number of buckets. Let's show you an example so that you can understand. So let's take this sentence. So here we have, maybe we have other tokens that come before, and here maybe we have tokens that come after. Let's say that max relative distance is set to 4, and let's take the word or the token not in this sentence. So here I said that we will have positive distances, and we will go up to max relative distance, which in this case is set to 4, and we have negative distances. So this range is called the number of buckets, and it contains unique learned bias values. So this is the range that we are interested in, because as I said before, tokens that are very close to the one that we are looking at will influence it more than far away tokens. So tokens that are very far away, that have very big distances, should not affect the token very much. Now, what do we do with the tokens that are outside this range? These ones will have shared biases. What bias do we take? So let's take the tokens that are on the left. These ones will use the first value from the unique learned bias values. And the ones that are here on the far right will use the last value from this range. This way, the model does not learn absolute positions, but learns how far apart two tokens are. Since this method is a little bit tricky to implement, I decided to make this diagram to help explain how the model uses this method. The diagram looks a little bit scary because it's big, but I'll try to make sure to explain each part individually so that you can understand the full picture. We start with a sentence. In this case, the sentence is, "Hi Imad, how are you doing?" We split it into individual tokens. Here we have 6 tokens and 1 sentence. This is the input shape. 1 is the batch size, and 6 is the number of tokens in the sequence. So after doing this operation, we are going to pass this tensor into the token embedding table. After that, we get a tensor of size 1 by 6 by 768. 768 is the embedding size. And here the block size is set to 1024. So this is the input. Now we need to feed this tensor to the attention layer. Here we have 2 individual parts. The first one is the multi-head attention layer, and the second one is the layer where we are going to compute the relative bias that will be used after. But let's focus on the multi-head attention layer, because I don't want to show a lot of heads because the diagram will be too complex. I have decided to show just 2 heads, and everything is explained in the first head, but the second one is, I don't show a lot of information because it's the same thing. When we take this input tensor and feed it to the head, we are going to create 2 tensors of the same size. So we have the key tensors and the query tensors. And here I said that we will create a tensor of the same size, but here you can see that the shape is not the same. So here we have 1 by 6 by 384. So 384 is just this value divided by the number of heads. Since we have 2 heads, we will divide 768 by 2. This will give us 384. So we create these 2 tensors, k and q. We transpose k to get this tensor. So the shape is 1 by 384 by 6. After that, we multiply these 2 tensors, and at the end we get a tensor of size 1 by 6 by 6. We do the same thing for the second head, and we stop here. We don't continue. We go back to the layer where we calculate the relative bias and do this. First, we create two position vectors, one for queries and the other one for keys. And here the size is 6. So we have 1 as the batch size and 6 is the number of tokens. So we take these two tensors and we use broadcasting to compute a 6 by 6 matrix. I think this is too small, so let me go back to Inkscape where I created this diagram and zoom in so that you can see this clearly. Okay, so this is Inkscape, and now I think you can see clearly. So I said we start with two tensors, one for query and one for keys. We use broadcasting to compute a 6 by 6 matrix from these two tensors, and this one is called relative positions because this matrix will have the relative distances between every pair of tokens. The diagonal contains zeros. The upper triangle of the tensor contains positive distances, and the lower triangle contains negative distances. Now we take this relative positions tensor and we shift it and clamp it. Here I am not showing a lot of detail, but don't worry, when we are going to switch to VS Code, I will show you everything that goes under the hood. After clamping, we are going to have values between 0 and a maximum value. That maximum value will be the number of buckets minus 1, but as I said, I'll not go into details. Why are we clamping the tensor? Because we cannot use negative values to get vectors from the embedding table. This will give us an error. So we need to have positive values to do that. So we take the values from here, we get the vectors from the embedded table, and we create this tensor. You can see that the shape here is number of heads by 6 by 6. This is very important because if I go back to the multi-head attention layer, you can see that the input is 6 by 6. And because we have two outputs, the shape should be number of heads, which is 2 by 6 by 6. So this matches what we have up here. Now we take each slice and we add it to the output of each head. So let's take this slice as an example. And here we take this tensor, we add them together, and the output should stay the same. It should be 6 by 6. After that, we continue. From X, we get the value tensor. We multiply these two together. We get the final attention weights. We do the same thing for the second head. We concatenate the results. And as you can see, we are back. And here, output and X have the same shape. So this is how relative positional encoding is implemented. I hope that this diagram was helpful, and now let's go to VS Code to see how to turn this into code. Here is the same diagram. I'll keep it here because I need to explain to you how this works. And instead of model, I have another script called model relative positional encoding. Let me put this one here. So I'll make this a little bit smaller. I hope it's not too small. And now let's go down. Here is our class. I added a new parameter to the model, max relative distance. We pass it from the GPT language model class to the block. After that, inside the block, we pass it to the multi-head attention layer. And here we start implementing the relative positional encoding. First, we start with number of buckets. Number of buckets is 2 times the relative distance. Remember, why are we multiplying this with 2? Because we have positive and negative distances, and we add 1 to take into consideration the distance 0, because if you are looking at the same token, the distance should be 0. So this is the range. I call this in the slides unique bias values. And after that, we create the relative attention bias embedding table with shape, number of heads by number of buckets. And it's this one. Let me zoom in a little bit. So you can see that here, this is exactly what I have here in the code. You can see that here we have number of heads and number of buckets. Currently, we haven't done any calculations, so let's back up. Here, I need to go inside the forward pass. So here, I am going to start with relative bias calculation. Here, I am going to get the relative bias, which is basically this yellow tensor or this green tensor. So I have this compute relative position bias method that I am going to use. And here you can see that let me zoom in again. We have two tensors, query positions and key positions. Here they are. And we are going to have a tensor of shape 1 by sequence length or batch size by sequence length. Okay, so we have query and positions. This is how we create the relative positions. So the shape will be t by t. Here it was 6 by 6, but in general it should be sequence length by sequence length. And here is how we do that just by using broadcasting. So we take key positions and we subtract key query positions. If you don't understand this notation, don't worry, I will show you how this works. So I will open my terminal. Here I will type Python. Let's start from the beginning. Let's import PyTorch. Here the sequence length is set to 4. This is just an example just to show you how this works. I will also create the key tensor and query tensor. So let's look at them. Key positions. This is the content of key positions and key query positions. Now let's run this code, relative position. So let's look at relative position. As I have mentioned here, the diagonal should have zeros. That's what we have here. The upper triangle contains positive distances. Here they are. And the lower triangle contains negative distances. Now I said that after computing this relative position tensor, we need to shift it and clamp it. So this is the first operation, which is shift the range to positive values between 0 and 2 times max relative distance. And this is how we do it. We take relative position and we add to it the max relative distance. And in this case, max relative position, it's not defined. We should pass it when we create the model, but let's just add it here. Let's say that max relative distance is, maybe we want to look at just two tokens, before and after the token that we are looking at. And we are going to take that. So let's take relative distances and we are going to add to it this value, max relative distance. So it tells me that relative index is not defined. That's correct. Let's create it again. Relative indices is equal to relative position plus max relative distance. Now let's look at both tensors, relative position and relative indices. And as you can see, things are shifted. So max relative distance is equal to 2. So the diagonal before was 0, now it is 2. So basically we added 2 to every value in this tensor. But we need to clamp it. So this is the second operation. And here is how we do that. So let me take this. And as you can see, here we no longer have negative values. Let me show you how relative indices was before. Relative indices. You can see that in this position, we have -1. After clamping that tensor, we have 0. And here we had 5. And because this is the max value, which is here 5 minus 1, which is 4, this value was clamped to 4. Why are we doing this? Again, just to remind you, because after that, we are going to take these values and try to get the embedding vectors from this embedding table. And we should not, because here, this is these are the positions. So buckets goes from 0 up to number of buckets -1. And here, if, for example, if you try to get a vector at position -1, you will get an error. Or if you try to get a vector at a position higher than the maximum position, you will get another error. This is why we need to do this operation, shift and clamp. Okay, so now we have the relative indices. Now we are going to use that table, that embedding table, to get the biases, and we are going to permute the dimensions, because this gives us t by number of heads. And as you can see from the output, we need to change that to be number of heads by t. So we do that with the permute method, and you can see that here 2 is basically number of heads. We put that at the first position, and we put t by t at the last positions. After that, we return that bias. This means that we return this. Okay, so here they are. So relative bias is this tensor. Now we loop over the heads, and for each head, we take one slice from this tensor. It's this arrow that goes here. We take one slice and give that to the head. Now let's go to the head class to show you how that works. So here is the head class. Inside the forward pass, we get the input, which is this one, x, and we get the head bias, which is one slice that we get from this tensor. Okay, so now let's look at head 1. You can see that we get key and query from the input x. We transpose the key tensor and we multiply it. Here we are using matrix multiplication. We multiply it by q in order to get the weights. Here they are. Now, before continuing, we are going to take that slice. It's here. We got it from the previous step. So we are going to take that weights tensor and add to it the head bias. And here we are using unsqueeze because head bias is going to be t by t. And we need to add the batch dimension so that broadcasting works. So after doing this, we are going to continue like before. We are going to have to use maxed fill so that we only keep the lower triangle in the tensor. After that, we apply softmax, dropout, etc. And then we come to this part. So we get the value tensor and we multiply it by the weights in order to get the output from one head. And after that, we just concatenate the results. And this is done in the multi-head attention class. So at the end, let's go here in the forward pass. This is where we were. So for each head, we take one slice from this tensor. We get the head output, which is this one. We append everything, but at the end, we concatenate those tensors in order to get the output. In this case, it will be of shape batch size by sequence length by embedding size, which is similar to the input tensor. So yeah, this is how you implement relative positional encoding. And again, I have created another notebook to, let's look at it, relative positional encoding, this one, to use this method and to get the training and validation losses. Now, let's look at the results in the slides. Okay, so I have explained everything here. Okay, so relative positional encoding. Again, we have training and validation, and you can see that relative positional encoding performed really well on both training and validation. So you can see relative positional encoding is this one. It has this plus icon or plus marker, but the downside is that it is slow because you saw we have a lot of calculation performed under the hood. It took 5 hours, and if you remember, the previous method took 2 hours to train. But it is worth it because we got so far the best performance. Now, we have one more method before we end this video, which is rotary positional encoding. So let's look at that. This method does not add any new parameters. That's a good start. Instead, it modifies the key and query vectors by rotating them before calculating the attention. I took the previous diagram and made it a little bit simpler, or I have adjusted it to work for rope. And I think this is a great idea to explain how the method works under the hood instead of just showing you the code. So let's start. How does this work? You can see that here, the only thing that you need to change is this. When you create the key and query tensors from the inputs, you will rotate them before calculating the attention weights. So when we are going to go to VS Code, we are going to focus on this part. So don't care about the other parts, just look at this one. You can see that here, this icon means that we are going to rotate that tensor. Let's go to VS Code and let's search for model rope. Okay, let's go down to the GPT language class. You can see that I have added a new parameter called rope base frequency. It is equal to 10,000. I took this from the Reformer paper. So they are using this to compute the frequencies. We are going to look at this later. And here you can see that I have also added this rotary positional embedding class, which will compute those embeddings or those frequencies. And we pass that to the block. We will do the same thing as relative positional encoding. Later, we are going to pass it to the multi-head attention layer. But before looking at the block, let's understand what is happening inside this class. Okay, so in the init function, you should understand that the rotary positional encoding method treats pairs of numbers as complex numbers. This is why we are going to loop from 0 up to embedding size divided by 2, because we are going to take two values from the embedding dimension and consider them as one complex number. Now, each frequency value is calculated like this. So you have theta at index I, so it's equal to 1 divided by the base frequency, which is equal to 10,000, but you can change that when you create the instance. So yeah, this method or this formula was taken directly from the Reformer paper. And here, this is just a code to basically calculate this. And so yeah, as you can see, this one divided by the denominator, which is, yeah, it is calculated here. Okay, so after getting the theta e's, we are going to multiply those values with the position indices. So position indices, again, will go up to block size. And here, we are going to use torch.outer to get the frequencies. Now, if you don't understand what torch.outer does, let me again open the terminal, and here I will create two tensors just to demonstrate how that method works. Okay, so we have tensor A and tensor B. Now I am going to write torch.outer, and I'm going to pass A and B. And here is the output. Let's see how this first row was calculated. So you take 1 and multiply it by these values. So 1 times 4 will give you 4, 1 times 5 will give you 5, etc. Now to compute the second row, we take 2 and multiply it by these values. So 2 times 4 gives you 8, 10, etc. So this is how torch.outer works. Now let's go back to the code. Okay, so here we have two tensors. So A and B in this example are position indices and theta e's. And here, the vectors don't need to have the same shape. So if I go back to A, and instead of 1, 2, 3, I will just remove 3. Let's go back to torch.outer, and as you can see, that works. Here we have the same things. So position indices will be of shape batch size by block size, and theta is of shape batch size by embedding size divided by 2. So when we use torch.outer, we are going to get a tensor of size, block size by embedding size divided by 2. And this will give us the frequencies, and this is what we need. Now from this, we are going to calculate the complex numbers in polar form. This is the polar form. So cos m theta plus I sine theta. And torch.polar will do that for us. We will get theta e's, and this is what we want. So theta e's are computed only once when we create an instance of the GPT language model class. And this is similar to the sinusoidal positional encoding. There we used the sine and cosine formulas to calculate those positional encoding only once. But here we are computing these frequencies or these values that are called theta e's, each position only once. And we have a method which is called get theta e's to retrieve them later. So this was too much math, I know, but as I said, this was taken directly from the Reformer paper, but I wanted to show you that this exists in this script so we can look at it. And to understand, try to make examples like this with smaller numbers, with smaller shapes, to understand how does the math work. And yeah, because when creating any deep learning model, shapes are the things that are going to cause you a lot of trouble. You need to either do this by pen or paper, or open the terminal and try to create the tensors manually, see how the shapes work, and this will help you understand any deep learning model that was implemented by someone, or it will also help you create any deep learning model. This is the role of rotary positional embedding. Let's go back to GPT language model. I have it here, and then I pass it to the block class. So inside block, we pass it again to the multi-head attention layer. Here, inside the head, we get the key and query tensors from the input X. And again, just to show you where we are in this diagram, let's make this a little bit smaller. Let's zoom in a little bit. You can see that we are here. We got the key and query tensors. Now we need to rotate them. I have added this helper function, apply rotary positional embedding. So it takes the tensors, it takes the theta e's, and it will rotate those tensors. And after that, the rest is the same. So you get Q and K, you transpose K, you multiply it by Q, you get the attention layers, you apply the mask, you apply the softmax dropout, and finally you multiply this by V and you get the attention weights at the end. So the rest is the same. This is the interesting part. So apply rotary positional embedding. This is a function that I have outside that will do this rotation for us. The tensor X has this shape: batch size by sequence length by embedding size. We take it and we reshape it to be of shape b by t by d over 2 by 2. Why are we doing this? Because remember, when we computed theta e's, I told you that rope will divide the embedding size into 2 and consider each pair as a complex number. This is exactly what we have done. We have divided the embedding size by 2 and we created a new dimension. Now, after that, so this will give us x combined. We will convert this into a complex number. And now we will have b by t by d over 2. And this dimension will go because we are going to create the complex numbers. Again, if you don't understand how this works, you can come here and create a tensor. So let's do that. Okay, let's look at the shape. So it's 2 by 2. And I will unsqueeze it to add the batch size or the batch dimension. So now, so I need to type x equals x dot unsqueeze. Now x dot shape should be 1 by 2 by 2. So this is exactly what we have here. Now we need to reshape this. So let's take this. Now let's look at x combined. Let's look at the shape. And it's 1 by 2 by 1 by 2. So let's look at let's use this function. Let's put it here. And as you can see, let's look at the shape. So it's 1 by 2 by d over 2, which in this case is 1. And as you can see, we have complex numbers. So this is the real part, and this is the imaginary part of that complex number. Okay, so now we got theta e's. So they are here. Theta e's are complex numbers, so pre-computed complex frequencies of shape t by d over 2. You can see that here we are missing the batch dimension. This is why I used unsqueeze. And now the shape should be 1 by t by d over 2. Now we need to apply the rotation by multiplying complex numbers. So we do this by just a simple multiplication. So here x complex has this shape, theta e's has this shape. Broadcasting will work. And this will give us a tensor of this shape. So it's the same shape, but this will result in rotating that tensor in the complex plane. Now we need to go back to real numbers. So torch.view as real will give us that dimension back. And now we need to flatten the shape to combine these into one dimension. So you can see that here, flatten the last two dimensions to get the embedding size back. So at the end, x out will have this shape, b by t by d. And this is exactly what we have here. So the input was 1 by 6 by 384. After rotating the tensor, it should stay the same. Okay, so here the input was b by t by d. So the output should be b by t by d. And that's it. This is how you implement rope in Python. Again, I have created another notebook to do the experiment. So it's this one, transformer, where is it? Yeah, it's this one. So improving transformer rotary positional encoding. I'll make sure to clean everything because here I have created a lot of files. So I'll make sure to clean them and then push everything into my GitHub repository. In that notebook, again, I created the model. I have used this script to instantiate the GPT language model class, and I have the results. So let's go back to the slides to show you what we got. Okay, this is the slide. So now I am comparing all the methods. So we have absolute, no positional encoding, sinusoidal, relative, and finally rope. And as you can see, rope is this one. It's in yellow. And as you can see here, it was close to the relative positional encoding method in terms of the loss value at the last iteration. But here you can see during the validation, it's performed better. So both of these methods are really great. So relative encoding and rope are the best, but since rope took 2 hours to train, and if you remember, relative positional encoding took 5 hours to train, this means that this method, rope, is 2.5 times faster than relative positional encoding, and also it generalized really well. And this is shown by the lower validation loss. So this means that we are going to consider rope as the winner in this experiment that I have conducted in this video, just to show you that positional encoding is very important. So if we decide to not use positional encoding, we will get this blue line. So the loss will be here, and the same for validation. But just by adding positional encoding, we improved the performance of the model by a big margin. So you can see the gap between no positional encoding and rotary is very big. And the same for validation. So this means that, yes, positional encoding is very important. Yes, we have a lot of methods and we compared between them and we ended up choosing rotary positional encoding because it is faster and it generalizes well in validation. So yeah, this is the method that I am going to keep, and it is going to be used in the final version of the model in the final video. I hope you found this first video in this course helpful. It took a lot of time to make, so if you learned something, let me know, and see you in the next video. Hi everyone! In this video, we are going to focus on the attention layer. We are going to compare different methods that researchers proposed to improve the transformer architecture. In this video, I will make sure to show you the theory behind each method and how to implement it in code. And by the end, we will choose the method that achieves the lowest validation loss. If you forgot about why we use the attention layer in a transformer, let me explain that one more time. Attention is used to help the language model focus on the most relevant pieces of information in the input. In this video, we are going to compare the following methods. We have sparse attention, multi-head attention, grouped query attention, linear, local, and latent attentions. And here you can see that I have tried my best to link to the original papers where these methods have been published. So here, for example, you have sparse attention, and sometimes I link multiple research papers that have talked about that specific method. So if you want to go deeper, please make sure to click on these icons. They are all clickable and they will take you directly to the research paper. Let's start with multi-head attention. This method was introduced in 2017 in the famous Attention is All You Need paper. Again, so here is a screenshot of the first page of that paper. You can click on this image if you want to go directly to this paper in order to read more about it. MHA, which stands for multi-head attention, is the foundational attention mechanism used in that paper. Here is the transformer architecture diagram, and here is the attention layer. You can see that it comes after encoding the input sequence. Here, in that specific attention is all you need paper, we were using positional encoding and word embedding or token embedding to encode the input sequence. And you can see the attention layer comes after the encoding and comes before the feed-forward network. The role of MHA is to compute the attention scores, and it does this independently across multiple heads in parallel. And this is the beauty of this technique, is that we can divide the computation into multiple heads and perform that computation in parallel, which speeds up training a lot. But you might ask, why should we use multiple heads? Can't we just perform a big matrix multiplication instead of dividing that into smaller matrix multiplications? The answer to that question is that when we use multiple heads, the model learns diverse representations because each head focuses on various input aspects. So maybe this head will focus on something, the other head will focus on something else, and this will help the transformer model generalize better. Now, let's zoom into the attention layer. Within each head, the input is projected into three matrices. We have the query matrix, the key matrix, and the value matrix. This diagram contains 6 heads. The first head contains the 3 matrices that I have talked about. And here, before we go to the second point, this arrow indicates that each query vector is compared to all key vectors to measure similarity. Here, when I say query vector, it means that I am taking a slice from that matrix, because the query matrix, it has multiple vectors. So we take one vector from query and we compare it to the other vectors to measure similarity. And here we measure similarity with by using dot product or other methods. This similarity measurements that we are performing gives us the attention score matrix. And here's how it looks like. You can see that this matrix is a square matrix. So basically here you can see that this is a full matrix. So here this means that we attend from both directions. So if I am at this token, I can look at the tokens that come in the future. For example, if I am here, I can look at the tokens that are before me and the tokens that will come in the future. But the problem is that here we are using a decoder only transformer. We are using that for text generation. This is the task that we are trying to perform. So we shouldn't look at the tokens that come in the future, because the model will cheat. So during training, we should apply a mask to remove the tokens that come in the future. These cells that are colored in white contain zeros. This means that the model will not be able to cheat because it doesn't have that information. And here the colored cells in this pink color contains the actual attention scores. By using this trick, we will ensure that the model learns how to predict the next token instead of cheating. Okay, so now here is our diagram. I am going to zoom into one head, but the calculation is similar to the other ones. Here is the formula that we use in order to compute the attention scores, and here is the diagram. This is exactly the steps that we are going to follow when we are going to implement multi-head attention in code. Here we have the input. We project that into 3 matrices: query, key, and value. Let's look at this term inside the softmax function. Here we have Q. We multiply that by the transpose of K. So here is K. We transpose it and we multiply that by Q. So here, after multiplying these 2 matrices, we divide by this term just to scale the numbers inside the matrix. I am not showing here, but I'm not showing that division here, just to keep the diagram simpler, but we are going to add this in the code later. After that, we get this matrix, which is basically this term. After that, we apply the masking, as I said, because we don't want to look at the tokens that come in the future. So we multiply this with V. and we get the output, which contains the attention scores. And here you can see that this multiplication is performed on the first head, and we perform the same calculation on the other heads that remain. And at the end, we take the output from each head and we concatenate them to get the full attention scores matrix. In this video, we are going to consider multi-head attention as our baseline. Here are the loss curves for both training and validation. Later in the video, we are going to compare the other methods to this baseline, because multi-head attention is the method that we used in the first course, and now we want to try the other methods to see if they improve the performance of the transformer model. The first method that we are going to compare against multi-head attention is multi-query attention. This method was introduced in the Fast Transformer Decoding paper. Click on the image if you want to read more about that paper. Multi-query attention is a computationally efficient method. Why? Because it reduces the memory usage by shrinking the KV cache. If you are not familiar with this term, KV cache, it means how much memory the key and value matrices take during training or inference. MQA uses one key and one value for all query heads. We have seen this diagram when I was explaining multi-head attention. You can see that in each head we have three matrices: key, query, and value. In MQA, all queries share the same key and value matrices. This means that K and V are calculated only once and then shared between the query matrices or between the heads. This means that the number of parameters will decrease, which might in turn impact the model's performance in some cases. But the major benefit of MQA is the inference speed. This method is way faster than MHA when generating tokens. Let's look at the internals. Same as before. We have our diagram, the attention function, and here is the diagram that shows what goes inside one head. Do you see a difference? The key and value matrices are outside the head. This means that they are calculated once and used inside each head. This is the only difference between MQA and MHA. You can see that the rest is the same. We perform the multiplication, so we compute this term inside the softmax function. We get this matrix, we apply masking, and after that we multiply it by V to get the attention weights. And this calculation is performed similarly on the other heads. It's comparison time. We have the two graphs for training and validation. In both cases, MQA performed better than multi-head attention, which is surprising. The difference is not that big, but it is in favor of MQA. I say that it is surprising because multi-query attention uses the same query and value matrices for all query heads, which means that we will have less diversity when training this model. But in this dataset that I am using, it seems that MQA worked better than MHA. But again, the difference is not that big. I have also mentioned that MQA is faster in inference than MHA, and here is the diagram that I have tried to create in order to illustrate this. You can see that here we have in the x-axis the number of tokens to generate. So I have tried to generate 100 tokens up to 2000 tokens for MHA and MQA. And here on the y-axis, we have the inference speed or the inference time in seconds. You can see that MQA is 7 times faster than MHA when generating 100 to 200 tokens. But after increasing the number of tokens to generate, that benefit starts to shrink. You can see that here at this point, MQA becomes 6 times faster than MHA. Here it starts to decrease again, so it's 1.7, and when we reach 2000, it became worse, so it's 0.8 times worse or slower than MHA. In the fast transformer decoding paper, where Noam, this researcher who worked on MQA, showed that this method was 12 times faster than MHA with a sequence length equal to 128 tokens. So this matches what we see. I mean, there he was using a very powerful hardware, and here I have just an RTX 4070, which is not that impressive, but still you can see that here. So he used 128, here I have 100 tokens, and here I got 7 times faster inference speed. And this, again, the model here is small, so if I increase the model size, this value will have changed also. So but this matches what Noam observed when he was writing that research paper. And here it's surprising that MQA becomes bad when we increase the number of tokens to generate. Maybe my implementation is not optimized, but since Noam didn't try to compare the inference speed at higher number of tokens to generate, I can't say 100% if this method works only when we generate fewer tokens, and it works bad when we try to generate large sequences of text. Now we have compared the performance of MQA to MHA. Now let's see how to implement this in code. I am in VS Code, and here I have opened the diagram. This is exactly what I have showed you in the slides. Let's put it here because it will help us see what we are doing inside this script. I will make it smaller. Open model multi-query attention, and like the previous video, everything will stay the same, but we are going to change just what we are concerned with. And here we are going to change the attention layer. So here I have created this multi-query attention class, and inside it, in the constructor, we have the number of heads, the head size, and here are the matrices. So we have the key matrix, value, and query. Okay, and we have the rest of things. We'll come back to the rest. Okay, so in the forward pass, now I will zoom in. We get the batch size, the sequence length, and the embedding size from the input. Here we compute the key and value matrices, and after that we get the query. So here everything is the same, but I have said that K and V are shared between all query heads. So after getting the query, you can see that here is the shape. So it's going to be batch size by sequence length by number of heads times head size. So we are going to reshape this to add the number of heads dimension. So here we have batch by number of heads by sequence length by head size. You can see that here this represents all query heads, but remember that we have only one key and value head. We are going to also reshape K and V in order to add this dimension, but we are going to put 1 because this is what I said. In multi-query attention, we have just one key and one value, and those are going to be shared by the query heads. We are going to use broadcasting to multiply K and V so that we can multiply them by Q. So let's see how to do this. So this is the only thing that we need to do. So here, when we are going to compute the multiplication between query and the key, Python will use broadcasting to make sure that the shapes match. So here, when we perform this operation, you can see that we cannot do it because here we have B times number of heads, and here we have B times 1. Python will try to match these two dimensions by multiplying the key number of heads times. So here we will have B times number of heads. And this is why I said that repeat for each head. Okay, and the rest will stay the same. So here we multiply Q and K. We divide by the head size. So this is the scaling factor. After that, we are going to, so here, let me zoom in again. We are going to perform the masking. We are going to use the softmax function, apply dropout, and at the end, multiply the masked weights matrix with V. So V, we are getting it from here. And again, you can see that here are the shapes. So attention weights is B times number of heads times T, but V is B times 1. So these two dimensions do not match. But luckily, Python will use broadcasting to solve this issue for us. So it will just keep duplicating V, number of heads times, so that this matrix multiplication can be computed. And at the end, this is the shape that we are going to get. Here you can see that we have tried to merge all heads into one simple class instead of dividing this into multiple heads and then concatenating the results of each head. By the end of this forward pass, we have everything concatenated. So you can see that here we transpose the first and second dimensions so that we can basically merge the number of heads by head size into one dimension, which is the number of channels. And after that, we are going to return the output, which contains the attention weights. This is exactly what we need to change, just the attention layer. The rest will stay the same, okay? And like before, like in the previous video, I have created a notebook to try this. So it's this one, improving transformer multi-query attention. And here, all I did is that I imported the GPT language model class from this new scripts that I have created. And yeah, the rest is the same. So here we divide the data into training and validation. And then I run this. And at the end, I make sure to save the training and validation losses so that I can print the curves and show them in the slides. Now let's go back to the slides in order to explain the next method. Local attention is the next method that we are going to focus on. It was mentioned in these two papers. Here they are. Again, you can click on them if you want to go deeper. Local attention works by limiting the attention span of each token to a fixed size window. Here is the full attention scores matrix, and this is how it looks after applying a window size of 3. You can see that in this case, a token can attend up to 2 positions in the pass. If I am, for example, here, I can only look at the 2 previous tokens, but you can play with this value. This makes local attention efficient, but it's a bit tricky to get the most out of it. You need to do a lot of optimizations to benefit from this approach. The problem with limiting the attention span to a fixed window is that long-range dependencies are not captured because the model is focusing on the local context only. Also, this method, like MQA, multi-query attention, might lead to a degradation in the performance of the model. Let's see what happens inside one head. We have our formula and here is the diagram. It is similar to the previous ones. The only difference is here. You can see that when we apply the masking, we make sure that we also apply the window so that we also turn the other values here in this lower triangle to 0. So we will have 0 here, and the values in the middle will have the attention scores. And finally, we multiply this masked attention weights with the V matrix in order to get the output. Now let's compare local attention to the previous methods, multi-head attention and multi-query attention. Here are the two figures. And as you can see, local attention is beating the other two methods in both training and validation. So you can see that the difference between local attention and multi-query attention is minimal. But if we compare local attention to the baseline, which is in this case, the standard multi-head attention, you can see that the gap is starting to increase. Here is the inference speed. You can see that local attention is not as fast as multi-query attention. So you can see it's even worse than multi-head attention in this configuration that I have tested. We also have other variants of this method. So here we have dilated slide-in window. This is how it looks like. We also have chunked slide-in window. This is how it looks like. We can also combine between the two. So we have global plus slide-in window. Here is how it looks like. So we still have the slide-in window, which is what I showed you earlier, but we add these global, you add these for the tokens that should be, that should attend to all the tokens. For example, the special tokens, like the start of text, end of text, etc. Okay, now we have seen the results. Now let's see how to implement this in code. Here is the new script that I have created, and here is the diagram that explains how local attention works. Here we have the three matrices, key, query, and value. Here they are just linear layers, but we are going to use them in the forward pass. Okay, so let's start. First, we have the input X. We are going to project it into the key and query matrices. So here we are using the key and query linear layers, and the shape will be batch size by sequence length by head size. This time I have the head class, but like the previous method, which was multi-query attention, we can combine them inside the attention class. It's up to you to decide, but it's similar. When you add the head class, at the end you will need to concatenate the results. But if you want to remove the head class, you will do everything. So instead of having 3 dimensions, you will have 4 dimensions. The first one will be batch size, and the second one will be the number of heads. Okay, so now we get these two matrices. We are going to apply our formula. By now you should know it by heart. Now we are here. We have the full attention weights that we got here. Now we need to apply this slide-in window masking. So how do we do this? Like what I did in the previous video. If you don't understand how this is implemented, the easiest way is to open the terminal. Let me activate the environment, and here open a new Python session and start experimenting with this. So for example, here, if you don't understand, okay, let me remove this because I don't have enough space. So if you don't understand, for example, what is happening here, how are we generating this matrix, you can come here. For example, here I need to import PyTorch, and here try to create small examples. For example, let's set t to 4, and here I need, so I will just take this. I will not take the device. Let's take unsqueeze. Okay, let's look at row indices. Okay, so here we have 4 rows and 1 column, and column indices should be similar, but instead we will have 4 columns and 1 row. Column indices. Let's look at column indices. Okay, so as you can see, we have 1 row and 4 columns. Okay, so why did we create these two tensors? Well, here is the first step. We are going to prevent the attention to future tokens. Okay, so how do we do this? If I take this, and again, look at causal mask, as you can see, here false means 0 and true means 1. So we can see that by doing this, we were able to remove the upper triangle from the, so this is the mask. We are going to multiply this with our attention weights matrix in order to remove the upper triangle. And how did we do this? You can see that here we have 4 rows and 1 column. Here we have 1 column and 4 rows. And this is the beauty of Python. So Python under the hood will use broadcasting in order to duplicate one of these tensors so that we can perform this operation. And this, because here we have 4 by 1 and here 1 by 4, this will be multiplied 4 times so that we get a 4 by 4 matrix. If you don't do this, you will never, it's going to be hard for you to understand this just by imagining it. You need to open the terminal, open a Python session, and tinker with these values or with these expressions that are in the forward pass. This is how you understand any model. Okay, so that was the first step. This is what we have done before, but now we need to apply that slide-in window. So here we have this parameter. In this case, because we have a small matrix, I will make sure to have a small window size. Let's set it to 2. And here, let's see the second step. So here we are going to create the local window mask. So this restricts the attention to a local window around the current token. Okay, this is what we have said. And this is the formula that we need to apply. So let's just take it here. Make sure to not take self. And here I need to add 1. Now let's look at local mask. And as you can see, we have everything is set to true. So the upper triangle is set to true, but the lower triangle is set to false. So this is the inverse of what we had before. Now we just need to combine the two. And we are going to use the AND operator so that we multiply the two values. So true times false will give us false. True times true, or true and true will give us true. So let's look at the final mask. Final mask. And as you can see, here is the upper triangle. It is set to false. This is exactly what we used to do before. But now we applied the local attention mask. And as you can see, we have two values max in each row. So this means that it works. And after that, we just need to apply this mask to the attention weights. And finally, after that, we use the softmax function. And at the end, we multiply the weights with the V matrix. After that, we get the output. And remember, this is just one head. So now we need to go. So this was already done, but I just wanted to show you this. So here are the full list of heads. Here in the forward pass in the attention class, we are getting the output for each head independently, but we need to concatenate them. So as you can see, the shape at the end will be batch size times time sequence or the sequence length times the number of heads times head size. This is how it works, and the rest is the same. Now I have also created another notebook where I have used this class, and this is how I was able to show you the comparison between local attention and the other methods. I hope that you understood this method. Now let's move to the next one. Grouped query attention is our next method. This one was mentioned in this paper. Training generalized multi-query transformer models from multi-head checkpoints. Click on the image if you want to read more about this paper. Grouped query attention is the generalization of multi-head attention and multi-query attention. This is the diagram for multi-head attention, and here is how it looks like for GQA. In grouped query attention, we try to form groups. In this example, we have 6 query heads, and we have created 2 groups. And in each group, the query heads share the same key and value. In multi-head attention, the number of groups is equal to the number of heads, which means that each head contains 3 matrices, key, query, and value. In multi-query attention, the number of groups is equal to 1 because all queries share the same key and value. But in GQA, we have the flexibility to change that value instead of being 1 or the number of heads. This means that grouped query attention offers an ideal trade-off between speed and performance. It falls between multi-head attention and multi-query attention. It is fast and also gives good results. When setting the number of groups to a value lower than the number of heads, GQA reduces the number of trainable parameters compared to multi-head attention. Let's zoom at the attention layer to see what happens exactly. This is how the diagram looks like for GQA. I want you to focus on this part. Here we are inside the attention layer. Remember that each group shares one key and value matrices. This means that we need to duplicate the K and V matrices multiple times to match the number of queries in one group. Let's take this as an example. You can see that in one group we have 3 queries, but we only have one key and one value. So if you try to multiply these 2 matrices together, you will get an error because the shapes do not match. And I tried to depict that with this change. So here you can see that query is bigger than v in size. So here we need to duplicate v and q multiple times so that we have the same size. And after that, we can apply this formula. So here, after duplicating k, you are going to transpose it, multiply it by q, and then apply the mask, and after that, multiply everything by v in order to get the output. But this is the important thing to consider when trying to implement this in code. Are you ready to see the comparison? Here you go. The model under grouped query attention has destroyed the previous methods. Look at the gap between the loss curves. It's huge. This method performed really well on both training and validation. And here I want to put a big asterisk on this result that I got. I have used a specific dataset for the Moroccan Darija. And maybe because here I took 1000 batches in both training and validation to basically draw these curves. Maybe I would have got different results if I have increased that value from, let's say, 1000 batches to 2000 or 10,000 batches. Maybe these curves will have changed, but here I am just showing you how to implement these methods, how do they work under the hood, and after that, if we change the dataset, we might get different results. Maybe I will try to rerun the grouped query attention another time just to verify that this result is consistent and update the graphs if I see something has changed. But here, as I said, the curves, each one will get different curves, each one will get different loss values depending on the model size and the data that you have used. Let's also check the inference speed. Here is the diagram. GQA is fast like multi-query attention, but it's a little bit slower than it. You can see that MQA is in orange. So yeah, the difference is not that big, but it's slower. Because here in multi-query attention, we have one group, but here we have more than one group. So we have more parameters than MQA. That's why it's a little bit slower. Now let's go to VS Code to see how to implement this. I have created this script, model grouped query attention, to implement this technique. Here we have the grouped query attention class, and let's see how it works. Here we have the classic parameters, number of embedding, number of heads, etc. But I also added the number of key value heads. Basically, this is the number of groups. So here I have this comment because, as I said, GQA is a generalization of both MHA and MQA. And here, if number of KV heads is not specified, we are going to set it to the number of heads to fall to MHA. But yeah, we shouldn't do that. We should specify a value greater than 1. And here, if number of KV heads is equal to 1, that means that we are going to use MQA. Otherwise, it's GQA. So number of KV heads should be greater than 1 and less than number of heads. So after that, so we are storing it here. We get the head size and the number of queries per KV head. We saw that in the slides. We had 2 groups, and in each group we have 3 queries, and this value stores that information. I will go directly to the forward pass so that we follow the diagram that we have here on the right. So from the input X, we project it to get the query, and here is the shape. So we have batch size, sequence length, and number of embedding. After that, we are reshaping the query to have this shape, batch by number of query heads, by sequence length, by head size. And here is how we do that. It's simple. We get those values that we got from the constructor and apply the transformation. After that, we get the key and values. And here, remember, so V and key are small because in each group, all the queries share the same key and value matrices. So we get the key matrix like this. We have this key matrix that we have defined here. It's a linear layer. And the shape will be like this. Batch size, sequence length. And here, the last dimension is number of KV heads times the head size. And remember, number of KV heads is the number of groups. So here we will have 2 keys. So here I am referring to the example that we have seen in the slides. So query, we will have 6 query heads, and here we will have 2 key heads. And because the number of groups is set to 2. So we are going to reshape this again to separate the head size from the number of KV heads. And we are going to do the same thing for V because they are similar. So again, V is, we are going to use the value matrix to project X to get the V matrix. And after that, we are going to reshape that tensor. And now this is the part that I have highlighted in the slides. So from here, we need to duplicate V multiple times so that we match the number of queries that we have. In that example, we have 6 queries and 2 values because we have 2 groups. So we need to multiply V and Q 3 times. So we are going to multiply 2 by 3 to get 6 value heads and 6 query heads. And this is the role of repeat KV. So this function that I have defined, I will show you what it does. We'll take one of these matrices, so K or V, and it will multiply it number of queries per KV times. And number of queries per KV is equal to 3. So 2 times 3 will give us 6. And this will match the number of queries. Okay, so let's go inside repeat KV to see what is happening. We have the tensor and the repetition times. How many times do we want to repeat that tensor? So if repetition times is equal to 1, we are going to return that tensor. There is nothing we need to do. But if this is greater than 1, we have this lovely function that PyTorch provides us. It's called the repeat interleave. And this will take, so you take the tensor, you call that method, and you tell it how many times you want to repeat it. And here we are specifying the dimensions that we want to repeat. Okay, so here we have number of KV heads, and this is what we want to repeat because number of KV heads is equal to 2 because we have 2 groups, but we want to multiply that to get 6 at the end. After that, this should be the number of query heads. This is why we targeted this dimension specifically because we want it to go from 2 to 6. To the total number of queries that we have. So this is a really great function that simplifies things. If we didn't have it, we had to do a lot of gymnastics to get this output. So yeah, this is what we have inside the repeat KV, and we use it for both key and value matrices. So yeah, now everything is prepared. The rest is the same. So we apply the attention formula, we get the weights, we apply the mask, softmax, we add a little bit of dropout, we multiply the masked matrix with V to get the final output, which in this case is Y. But remember, since we have 4 dimensions, we need to merge the number of query heads and head size. And this is exactly what we are doing here in these lines. And finally, we apply another dropout and get the final output from this grouped query attention class. Yeah, and again, here you see that we didn't use the head class, so we have merged everything into the attention class. And as you can see, sometimes I show you how to use the head, so if you want to perform the calculations separately, you can do that. And sometimes I show you how to merge the head inside the grouped attention into the attention layer. And whenever you fuse the head, you always add another dimension. When we don't have the head class, we will have 4 dimensions. But if we decide to add the head class, we will have 3 dimensions. And at the end, you concatenate the output from each head separately. And again, after I have created this, I have made sure to create a notebook that I have run in order to get those results. And you can find it here. So let me search for it. It's this one, 923, improving transformer grouped query attention. Now let's go back to the slides to learn about the next method. Linear attention is the method that we are going to focus on now. Read the following papers if you want to understand this method deeply. Again, you can click on the images if you want to get a direct link to the papers. We know that multi-head attention scales badly with long sequences of text because of the ON squared complexity. Linear attention tries to solve this issue by using less memory in order to be efficient. How does it do that? Well, researchers found a way to approximate the attention formula with this one. You can find this approximate equation in the paper that I have highlighted in the previous slide. And as you can see, here is the equation number 5 is exactly what I have written here. Also, researchers found that even though we are doing this approximation, which goes from big O n squared to ON, basically turning the complexity to be linear, they found that this method can give you good performance even with this approximation. Now let's see how the attention layer looks like. First, we have our linear attention formula, and here is our diagram. This time, the diagram is different than the previous ones. First, we have this phi function that we apply to the query and key matrices. This gives us phi q and phi k. Also, if you look at the formula, we can turn it into this. So Si is basically this summation and Zi is this summation. So we can also compute these terms. So we have already computed phi q, it's this one. Now we can compute Si. So Si is basically phi k times the transpose of v. So we are going to take phi k, here it is, and we are going to take v. Here I didn't show v transpose, but we should transpose it before multiplying it by phi k. This gives us Si. And Zi is basically phi q, phi k. So Zi is phi k. Now we need to multiply Si with the transpose of phi q. Here it is. So Si times phi q transpose. And here basically we need to multiply Zi with the transpose of phi q. And here it is. So Zi multiplied by phi q transpose. And after that, we divide the numerator with the denominator with this operator. And at the end, we get the output, which gives us the attention weights. You will see that this diagram will help us understand how to implement this in code. It will be a direct translation from these steps that you see here into code. Now let's compare linear attention with the previous methods. Here is the graph for the training loss and the graph for the validation loss. Because these curves are close to each other, let me zoom in a little bit so that we can see clearly. Linear attention is this pink curve, and overall, it's comparable to multi-head attention. So you can see here in validation, both MHA and linear attention are very close to each other. So even though it is comparable, it's not the best method in our benchmarking. But you can see that we have a method that works very fast and gives us the same performance as multi-head attention. Let's see the inference speed to verify if this is correct. So linear attention is this green bar or this light green bar. You can see here. Let's go to 2000 because here where we see the big difference. You can see that linear attention is super fast. And that's because it doesn't use a lot of memory. I have an RTX 4070 and I have 8 gigabytes of VRAM. And MHA was using almost 7 gigabytes while linear attention was using only 3. This is why this method is super fast. Now let me open VS Code in order to show you how to implement this in code. Here is the script that I have created. It's called Model Linear Attention. We have the linear attention class. And as always, let's go directly to the forward method because here we have the implementation. So first, what do? We project the input text into the 3 matrices. This is what we are doing in the first step. And here you can see that we have the phi function. Let me zoom in. Okay, that's better. Phi is defined like this. It's ilu plus 1. If you are wondering what is this function, basically it's an activation function. We have sigmoid, tanh, relu, etc. And ilu is one of them. So this was the activation function that the researchers have used in the research paper. So we are using that also. But if you want, you can change this and use other activation function. Now let's continue. We have the projections. Now we need to reshape, because again, here we are fusing the head into the linear or into the attention layer. So we need to have 4 dimensions instead of just 3. So we are introducing the number of heads at dimension. As you can see, this should be the final output. Batch size by number of heads, by sequence length, by head size. We have the projection, we have reshaped them. Now we need to apply the phi function to the query and the keys. And this is what we are doing here. So we take the query, we take the key, and we apply the feature map. This gives us phi q and phi k. Okay, so now we need to compute si and zi. So here is S cumulative. S cumulative is basically si. And if you, si is what? Is the multiplication of phi k with v. So here is phi k and here is v. And here we are introducing new dimensions so that we can multiply these two matrices. So here at the end it should give us, so here head size by 1, 1 by head size. So at the end it should be b by number of heads by t by head size by head size. And zi is just phi k. So there is no multiplication needed here. Okay, now we need to compute the numerator. So the numerator is basically si times phi q transpose. So here is phi q and here is si. That gives us the numerator. And here I try to also show you the formulas so that you don't get lost. Now the denominator is zi times phi q transpose. So here is z and here is phi q. And we also add an epsilon. Epsilon is a small value. I think here it is set to, let's see, it's set to 10 to the minus 6. We are adding the epsilon because this is the denominator. Let's say that this term was equal to 0. We shouldn't divide by 0 because that would give us infinity. So we add that small value to prevent that from happening. And at the end, we get the attention weights, which is the numerator, which we get from here. We divide it by the denominator. And finally, because we have 4 dimensions, we need to fuse those into just 3 so that we get batch size by sequence length by the number of heads times the head size. And finally, we apply the projection and dropout to the output so that we get the dimension that we are looking for. Okay, so this is how you implement linear attention. And if you are wondering, I also have created a notebook to run it. It's 924 Improving Transformer Linear Attention. Now let's go to the slides to learn about the next method. Now let's talk about a paper called Big Bird, which introduced sparse attention. Click on the image if you want to read more about the paper. Big Bird is designed to process large sequences of text without sacrificing the performance. Big Bird uses sparse attention, which is designed to reduce the computational and memory complexity to be linear. We call this big O of n. Sparse attention is the sum of global attention, which looks like this, random attention, and the sliding window attention, which we also call local attention. This gives us Big Bird, which is sparse attention. We have seen that when we used local attention, we were capturing only local dependencies. But Big Bird, because it uses this mix of attentions, let's call it like that, it captures both global and local dependencies. Let's zoom into one head to understand how to implement sparse attention. You can see that the diagram is big, but it's simple. Let's start by computing the weight matrix as we did before. First, we take the input, we project it into the 3 matrices, and then we compute what we have inside the softmax function. That will give us the raw weights. And now this is the change. So we need to create a mask in order to multiply it with the weights matrix. And this is what we do. Here we have the local attention mask. You can see that here we have zeros in the upper triangle and the lower triangle. We have global attention, which looks like this. And finally, the random attention mask. Here, this symbol means OR. So we are going to take these masks. You can see that the values that are colored in blue, or the cells that are colored in blue, contain the number 1 or true, and outside that we have false. When we use the OR operation, we are going to fuse these 3 masks into one mask. And as you can see, this gives us what we have seen in the previous slide, which is the sparse attention. And you can see that here we have a mix of global, local, and random masks. And here we also create the causal mask because we want to remove the future tokens from the mask. And here we use the AND operation. So AND, it's simple. If you have true and true, that gives you true. If you have true and false, that gives you false. By using this operator, we get this final mask. And now we take the final mask, we multiply it with the weights matrix. That gives us the masked tensor that we can then multiply with V in order to get the attention weights. Now let's compare sparse attention to the previous methods. Here are the 2 graphs. Again, because the curves are close to each other, I'm going to zoom a little bit. Big Bird is this light blue color. And as you can see, it performed good. The performance of sparse attention is good. So it's close to local attention in both training and validation. Now let's see the inference speed. But the problem is that Big Bird is slow because here we are combining multiple attention mechanisms and that slows down this approach. I mean, we can play with the hyperparameters in order to, for example, you can play with how many random cells you want to add, the size of the window, but overall, when you add all those attention mechanisms, you will get a slower solution. And because here, if I go back, here we do a lot of multiplications. So we have a lot of matrices that we need to compute before getting the final attention weights. That also makes the approach slower. It doesn't use a lot of memory, which is good, but maybe the implementation needs to be optimized. Now, let me go back to VS Code in order to show you how to implement this method. I have created this script, which is called model Big Bird, and we have the head class. So let's go directly to the forward pass and let's see what we have. So first of all, we compute the query and key matrices. Then we multiply them together in order to get the weights matrix. And now we stop. So we go down. Let me zoom in. And things might seem familiar to you because we have seen this before. In order to create this mask, we create two vectors or 2 tensors, row indices and column indices. We use this operation in order to get the causal mask, which is this one. After that, we are going to compute the local window mask. We get it after performing these operations. And this is exactly what we have done in the part where I have talked about local attention. After that, we have global mask. And here we need to specify the number of global tokens, because as you can see here, for example, we chose just 1 token, but we could choose multiple tokens. And after that, we have random attention that will give us this mask. And then, so we get here the random columns. Now we combine the local, global, and random. So here I forgot to add and random components. Okay, so you can see I am using the OR operator in order to combine those. And finally, when those are combined, I am using the AND operator to multiply the causal mask with the final mask. That gives me this, which is this value, this variable, final mask. Now I apply that to the weights matrix, and then I multiply that with V in order to get the output. I went very quickly. As I showed you before, you should not get scared if you see a lot of code. If you do not understand, always open the terminal. Let me activate the environment. open a new Python session and start playing with this. You should not get scared if you see a lot of code. For example, okay, so I am here. Let's create, or let's import Torch at the beginning. Now let's create small examples. There is no need to have big matrices. So small examples always help you understand the concept. So for example, here I am creating a random input tensor. Here the batch size is set to 1, the sequence length is 6, and the embedding dimension is 16. And now you can come here, for example, take this, paste it here, look at B, okay, that's 1, etc. And you can verify. So after that, I can come here, take this. So I need number of embedding. Let's set it to 16. Let's set the head size to be 8 so that I get two heads. And now I need to import an n. Let's get the key. Okay, now I can go back and use this. So now I can create the key matrix or the key tensor, give it x, and that gives me the k matrix, and I can look at the shape. Okay, so that makes sense. So k and q are of shape b times t times head size, and this is what I get. So this is the batch size, this is the sequence length, and this is the head size, and this is exactly what I have just set here. So head size is equal to 8. You can verify these just like that. It's hard to visualize these things in your head because there is a lot of code, and especially if you work with large matrices, that becomes very, very unintuitive. But choosing small examples will help you understand everything. Okay, so now you can do the same thing. Let me continue just a little bit. So again, I can go back. Since key and query are the same, I can remove this, replace that with query. I can get the query like this, and again I can look at the shape, and that gives me the same result. Now I can go down and compute the weights. So let's take this, paste it here. Let's look at weights. Let's get the shape, and this gives me 1 by 6 by 6, which is exactly what I have mentioned in the comments. So batch size by t by t. Now I can, for example, take this. I just want to show you the masks really quickly. Okay, so I don't need to have a device, but let me just set it to be CPU. Let's go back. Let's do the same for columns. Okay, and now let's get the causal mask. I know we have seen these things, but I just wanted to show you how to visualize everything. So you can see that the upper triangle is set to zeros, which is what we want. This is exactly the definition of a causal mask. And again, if I come here, let me set the window size to be 2, and let's take these conditions. Okay, here is the first one, here is the second one, and let's get the local attention mask. Now let's look at it, attention mask, and voila, as you can see, the upper triangle and the lower triangles of this tensor are set to 0. But here we have 2 values in each row that are set to 2. So this is the local mask. And here we also, if you want to create the global mask, as I told you, we need to set a number of global tokens. Let's set it to 2 because the matrix is small. So I can take this, put it here. I can do this for both query and key. And let's look at global attention mask. You might find this strange because we don't have a square matrix, but because here Python will always remember that Python uses broadcasting. So here you have 6 by 1. After that it will become 6 by 6, and everything will work. And also we can do the same thing here for random attention mask. So I have the value now. Okay, so here we have just created a matrix of zeros, but after that we are going to again specify the number of random tokens that we want to have. Let's set it to 4. Okay, so this gives me random columns. So this just will tell me where should I put those. Here I have the row selector. Sorry. I'll just go through this very quickly just to show you the final output. And as you can see here, for example, we have true in some other places, but as you can see, it's random. And now I can combine the two or combine the three. So I can take this and put it here, combined mask. Just a small trick, if you find it very difficult to see the trues and falses, you can use the .int method to convert that into integer. So as you can see, so this is the combined mask. So we have the global mask and we have some random values also. Let's do the same thing for random just to be able to see that. And as you can see, so everything is random. What you should take from this is that never get discouraged. You have the code in front of you. It's easy to use small examples in order to understand how things work and how the matrices looks like. And this is exactly why I add these graphics, just to show you how things are implemented, because you can easily find these steps in the code. So you can see that here the OR operation, for example, it's here. So you can easily find the step in the code, and everything should be familiar to you. And this will help you visualize the attention layer very easily. Okay, so after getting the output, as I said, because we are using the head, we need to go to the attention class, and here we need to concatenate the output of each individual head. And again, I have created, let's see, so where is it? 925, improving transformer big bird attention. This notebook, I have used it in order to import the GPT language model class from this script and in order to run the experiments. We are near the end of this video. We have one last attention method to look at, which is multi-head latent attention. So let's go back to the slides in order to understand how that one works. This is the final attention that we are going to look at. It is called multi-head latent attention, and it was introduced in the DeepSeek V2 paper. I highly recommend reading this paper because they have explained how they created this method or this attention mechanism in detail. They have showed all the mathematical equations, and even they have a graph that explains how it works under the hood. Click on the image if you want to read more about it. MLA is an efficient method that compresses the KV cache. We have talked about KV caching before. It means that you are going to store the key and value matrices, and this becomes a bottleneck, especially during inference, because if you are generating large sequences of text, you will need a lot of memory in order to store those matrices. So DeepSeek, with this method, they have showed that they can reduce this KV cache by compressing it. And the great thing about this is that it does not sacrifice the performance, and it guarantees faster inference. We have seen that methods like multi-query attention or grouped query attention also tries to lower the KV cache, but the problem is that the performance might degrade. But here with MLA, it guarantees both things. MLA incorporates latent representations into the attention mechanism. We are going to see this in the implementation. Instead of directly projecting the input X into the three matrices, we are going to project that into a latent representation, and from that latent representation, or we can also call it latent embeddings, we are going to generate our key, query, and value matrices. MLA is very fast compared to MHA. We are going to look at this in the inference speed test. Now let's see how this method is implemented. I want you to focus on these two matrices. So here, as I told you, instead of projecting X into the three matrices, key, query, and value, we are going to have an intermediary step. This is called compressed query, and this one is compressed key and values. From these latent representations, we are going to get the query, key, and value. And after that, the rest will stay the same. But this is the thing that was added, and this is shared by every head. And this helps reduce the KV caching, because you only need to cache these two matrices, and later you can generate the rest, because from from CQ we get Q, and from CKV we get K and V. Now let's compare the results. Again, we have the graphs for training and validation, and here multi-head latent attention is this curve. You can see that here in validation, it is very close to local attention. Again, take these results with a grain of salt, because we might get different results if we decide to change the hyperparameters or how many batches we include in the testing. And as you can see, we get results better than MHA, even though we reduced the KV caching. Now let's see the inference speed, because this is very interesting. So MLA is colored in black, and as you can see, so let's go to 2000 tokens, because this is where the other methods struggled. And as you can see, MLA, as I told you, is really fast. So we can generate a lot of tokens without sacrificing the performance. And here, the one that was very close to it, it's linear attention, because linear attention is also good, because as we have seen, it reduced the complexity to ON instead of ON squared, but MLA is the best. Now, let's go to VS Code in order to see how to implement this. I have created this script, model multi-head latent attention, and everything is implemented in this DeepSeek MLA attention. As I told you, I have been inspired by the research paper that they have published. There they have shared everything, so that was a great resource. And let me zoom in here, because we will need this diagram. Okay, let's get started. And here also I want to mention that these terms that we see here are basically the terms that they used in the research paper. Let me open that research paper so that you can see these things with your eyes. Here is the research paper, and here you can read the abstract and the introduction, and also the architecture chapters, because here they explained multi-head latent attention, and they have a good diagram that helps you understand how it's implemented. But I want to go to the appendix, because they have gathered all the formulas here. Okay, so now let me zoom in a little bit. And as you can see, here are the terms that I was talking about. So these matrices that you see here, for example, WDQ, WUQ, etc., are here. So you can see here is the WDQ, WUQ, etc. And the terms such as CQ and where is the other one? So you can see CQ and CQV. Here it is CQV. These are the terms that I have showed in the diagram. Okay, so let's continue. I just wanted to show you this because this is a little bit different from the other scripts that I have created. I try to make sure to use descriptive names, but since I was inspired by the research paper, I try to stick to it as much as possible. Now let's go to the forward method. Again, we extract the batch size, sequence length, and embedding from the input. Now let's start. So here we need to get CQ. So I called it compressed Q latent, and we get that from the WDQ. And WDQ means we are down projecting. And after that, we apply layer norm. This is what they have applied in the research paper. And after that, after getting CQ, we are going to project that back to UQ. We are going to project that to get the Q matrix. And here, if I go back to WUQ, you will see something interesting. We go from number of embedding to this compressed dimension, and WUQ, which is here I called up projection, will get back from Q compression dimension back to the number of embedding. So basically here we are making the matrix small, and after that we go back to the big matrix. And this is why this method is fast, because here we have a small matrix that compresses the knowledge into a small space. Okay, so these are the two matrices that we have used in the first place, in the first step. And after using WUQ, we get the Q matrix. Here I called it Q final. And we do the same for CKV. So we use this matrix. D means down and U means up. So we are going, again, if I inspect WDKV, you will see that we go from number of embedding to another small space. Okay, so that gives us CKV, which is this. And from CKV, we need to get the key and value matrices. This is exactly what we are doing here. After applying layer normalization, we use WU key and WUV in order to get those two matrices. And if you have noticed, we don't have the head class. So we need to introduce the number of heads dimension. We get QFinal, we try to extract the number of heads from the C channel or from the C dimension. I think you should be familiar with this. We have done this multiple times. I want to show you something new that I haven't used in the previous scripts, is this function scaled.productAttention. PyTorch provides this method that calculates the attention scores. So I just wanted to show you this because previously we were doing this manually. You can see that it handles softmax, scaling, and causal masking. So there is no need to do that manually. You need to give it the query, key, and value matrices. If you want to give it a custom mask, you can do that. But because here we are setting is causal to true, that will be handled by PyTorch. But if you want to provide another mask, just set it here. And here we are providing the dropout probability. After that, we need to concatenate these two dimensions in order to get just one. So we are going to get the C channel again, or the C dimension. Here we have this WO, which basically will give us the output. So we are going to project the attention weights into another matrix that we call output, which is basically this one, and we are going to return it. So let me close this file because I don't need it. And I have also made sure to create a notebook. So it's called 926, Improving Transformer Multi-Head Latent Attention. So here I have imported the GPT language model class from this script, and everything stayed the same. We have reached the end of this video. I really hope that you have enjoyed it. Before I finish this video, I want to show you basically what we have. The baseline was standard multi-head attention. We have used many attention mechanisms. We have compared them to the standard multi-head attention, and we have seen that all of them performed really well compared to standard multi-head attention. Here you can see that I have picked multi-head latent attention and grouped query attention for two reasons. We have seen that multi-head latent attention was super fast compared to the other methods, and it used less memory overall. And grouped query attention, you can see that here the gap is very huge, and this is on the validation set. But it was slower compared to multi-head attention. And here, I think that for some reason, grouped query attention worked really well because I have maybe used a small number of batches in the evaluation. As I said, I took 1,000 batches from the training set and the validation set as an evaluation set. Maybe if I increase that to, let's say, 5,000 or more, maybe this graph would have changed. But for some reason, maybe grouped query attention got lucky and we got this huge difference. But I think I will stick with multi-head latent attention because it's fast and it performed well. That's it for this video. See you in the next one. Hi everyone. In this video, we are close to finishing the course. So far, we have done a great job learning about the different attention mechanisms and ways to encode positions. Those were the big things in the transformer architecture. This is why I am calling this section small refinements, because we are going to do small experiments that test different normalization methods, different activation functions, is dropout necessary, for example, etc. Let's start. First, we are going to try different activation functions in the feed-forward network. Here is a graph that shows different activation functions like ReLU, GeLU, sigmoid, etc. In this video, I will pick GELU and SWIGLU. If you are wondering why I chose these two activation functions, basically because training large language models is expensive and I don't want to try every activation function that exists because the list is very long. After that, we are going to play a little bit with normalization methods. Currently, we have been using layer norm, but we also have RMS norm and batch norm. Although this one is not used in LLMs. Then we are going to compare placing the normalization layer before and after the attention and feed forward layers. We commonly refer to these as pre-layer norm. You can see that here, for example, I have the attention layer and normalization comes before it. And we also have post-layer norm. You can see here is the attention layer and normalization comes after it. And you can also do this for the feed-forward network. We are going to see this in the coding section. Finally, we are going to ask this question. Should we use dropout? In the previous code, I'm referring to the baseline. We have used dropout heavily in the code, but this time we are going to remove it and see if that improves the performance or not. This is the plan that we are going to follow. Now let's go through it. In the previous years, the most common practice was to use ReLU in deep learning for every problem. This is how ReLU looks like if you are wondering. But now, every LLM uses a different activation function. Why ReLU is not much used anymore? The problem is that negative values are clamped to 0. This limits the representational capacity of this activation function. Researchers created many activation functions that addresses this issue. For example, leaky ReLU is one of them, and here is how it looks like. You can see that leaky ReLU allows negative values to pass through to the next layer. The problem is that negative values can grow to large values, and we don't want that. Are we done? Is this a problem that is unsolvable? No, don't worry. We have another activation function, which is called CILU, and other activation functions. It's not only this one that solves this issue. You can see that here, instead of allowing every negative value to propagate, we are going to control the interval. For example, the values that are inside this interval are going to pass, but after that, we are going to clamp the values to 0. SWIGLU is an activation function that is used by the Llama model, and it is composed of two parts. We have swish and GELU, gated linear unit. Both of these are activation functions, and by combining them, we get SWIGLU. And if you are interested, here are the formulas for these activation functions. Swish has been shown to outperform ReLU in many applications, and GELU allows the network to focus on important features by either passing or blocking information. We have talked a little bit about the activation functions that we are going to use in this video. Now, let's see the benchmarking. We are going to consider ReLU as the baseline, because I have used it in the multi-head attention video. Then we will evaluate the performance of GELU and SWIGLU in comparison to ReLU. Here are the results. As you can see, SWIGLU is the winner. It converged quickly and it achieved the lowest loss value. Now let's go to VS Code to see what I have changed. The model script is our baseline. And if I search for ReLU, you will see that I have used it in the feed forward class. And this is the only place where we used an activation function, and we are using it between two linear layers. Here is the second script that I have created. Here I have used MLA for the attention method, and here I have replaced ReLU with GELU. And for SWIGLU, let me search for it. Yes, it's this one. Let's go down. This one is a little bit difficult to implement, but here I have been inspired by the code that is provided by Meta. Here it is. I have tried to select the parts that we are concerned with. And here you can see that they also use this inside the feedforward class. So let me go back to VS Code, and here it is. Remember that I have mentioned that Swiglo is the combination of Swish and GLU. GLU means gate linear unit, and here you can see that we have this gate linear layer, and we have two linear layers that will compress and decompress the inputs. But I won't go into detail because, as I said, I just took this implementation from the existing Llama code. But what interests us is how we can compare different activation functions and where you should change them. Most of the activation functions are implemented in PyTorch, but the new ones or the custom activation functions that researchers come up with maybe are not yet implemented, but check if they're already inside the NN module. For example, here I can search for, you can see that here we have different flavors of ReLU. We have ReLU 6. I've talked about CLU, Sigmoid. You can see that we have a lot of activation functions. So if you are wondering how to change the activation functions, here is where to do it. Now let's go back to the slides to talk about normalization methods. Normalization is a method that helps the network train quickly and stabilizes the training process. Normalization helps mitigate the issues of vanishing gradients and exploding gradients. Let's focus on vanishing gradient. Here is a simple diagram for a neural network. We have the input and output layers, and in the middle we have the hidden layers. The arrows indicate that here we have a forward pass. We take the input, we feed it to the hidden layer, and after that we get the output. Vanishing gradients means that during backpropagation, the gradients starts big and decrease from layer to layer. This effect starts to be noticeable when training networks with a big number of layers. Let's say that you have a network that contains 100 layers. By the time you reach the first layers, maybe the gradient will be equal to a small value, and that will make training very slow. Here is a meme that maybe will help you understand vanishing gradients. You can see that the meme says, "Me uses sigmoid and 10H activation functions, gradients." So the gradients start small and then they start fading, and by the end, they are gone. Exploding gradients, on the other hand, is the opposite. The gradients start small, but they keep increasing between layers. In any case, we don't want to deal with vanishing or exploding gradients. So it's great that normalization helps prevent this issue. Also, I want to emphasize that normalization adjusts the scale of the data without changing its shape. Here is a figure that explains this point. Here on the left, you can see that the values on the y-axis ranges between, let's say, 3 and 8. But on the right, after using normalization, the range has been changed to be 0 to 1. Same story for the x-axis. You can see that here we have maybe 25 to 70, but after that, the range is between 0 and 1. But the shape did not change, even though the scale of the data changed. There are many normalization methods. We have layer norm, batch norm, RMS norm, etc. Layer norm is the method used in the original transformer that was introduced in the Attention is All You Need paper. Here is the equation used by layer norm. This method normalizes the activations of each layer across the feature dimension. Here is a diagram that illustrates that. Here we have a tensor where n is the batch dimension, c is the feature dimension, and we might have other dimensions. For example, if you are dealing with images, you might have the height and width. It depends on the data that you are working with. But you can see that here the normalization is done across the feature dimension. In this case, it's C. Use this method if you can't use big mini batch sizes. In our example, we are training a large language model. Maybe we have few resources, so we cannot train on very big batch sizes because we don't have a lot of memory. In that case, maybe layer norm will not work. Batch norm, on the other hand, normalizes the activations across the batch dimension. You can see that here, instead of applying it in the C dimension, we are applying the normalization across the batch dimension, which in this case is denoted by this letter N. And here is the equation used by batch norm. Batch normalization uses learnable parameters in order to allow the model to shift and scale the normalized activations. So the normalized activations is basically this term in the middle, x minus mu divided by the square root of this term, and the learnable parameters are gamma and beta. Finally, we have RMS norm. This method normalizes the activations based on the root mean square of the activations themselves. Here is the formula that is used by RMS norm. Unlike layer norm, RMS norm does not center the activations before normalization. So you can see that here, let me go back. Here we have x, so the minus mu, so this is a term that centers the activations. But here, there is no term that will center the activations before applying the normalization. RMS norm reduces computational complexity without sacrificing performance. This means that training will be a bit faster, but the performance will not degrade. So I have explained to you the 3 normalization methods. Now let's start the benchmarking. Because I have used layer norm in the previous script or in the previous course, I will consider this as the baseline and I will compare RMS norm to layer norm. Here are the results. I had to zoom a lot in order to see which method did well. As you can see, layer norm performed better by 0.07%. You can see that the value is so small because there is, I mean, even though, yes, layer norm performed better than RMS norm, but because the difference is very small, it's not that interesting. And this confirms the points that I said in the previous slide, where I said that RMS norm reduces computational complexity, but does not degrade performance. Now let's go to VS Code in order to show you how to apply or where should you change the script so that you use other normalization methods. Here is the previous script that we used in the previous course. And if I search for layer norm, you can see that we have used it in many places. We have 3 layer norms that we defined. As we have seen in the section where we talked about activation functions, PyTorch comes packed with many normalization methods, and you can access them like this. So you use the NN module. Let me go down, and here we already saw layer norm, but if you want to use, for example, RMS norm, you can find it here. Let's search for batch norm as well. Here they are. And batch norm is used a lot when you develop CNN models. So this is why I didn't use it in this LLM course. But yeah, just to give you an idea, if you want to search for something, start by searching inside the NN module. Maybe you will find what you are looking for there. But if you don't find it, you can implement it yourself. So this is the previous script that we have used. We have used layer norm, so there is nothing we need to change here. But I have also created another script where I have implemented RMS norm. So here I have used again the same script that I have talked about. This is the llama script. So this Python script is used for inference, and in these lines they have implemented RMS norm. Here is the RMS norm class, And yeah, I've just copied this and I have pasted it inside my custom script. So yeah, this is how it looks like. And basically this implements the formula that I showed you in the slides. And you might ask, why did you implement it yourself? Doesn't it exist in PyTorch? Yes, it does exist, but I did not think that PyTorch has RMS norm. That's why I went searching for it, but I could just delete this and use nn.rms norm and that will have worked. But sometimes you might find new normalization methods that researchers have come up with, but you will not find them inside PyTorch. In that case, you need to create a custom class and use it. And if I search, you can see that here I have basically replaced every instance of nn.layerNorm with my custom class. Or in this case, we could just use nn.rmsnorm and that will have worked also. Now let's go back to the slides. Let's talk about where to put the normalization layer. We can place normalization before or after any layer. We use special names, pre-layer norm and post-layer norm. Here ln stands for layer norm, but if you use another normalization method, you should replace it with that method. We have seen these diagrams before. Pre-normalization means that the normalization method of your choice comes before the attention layer in this case, and post-normalization means that normalization comes after. Post-normalization can encounter stability issues as the number of layers grow. Also, it achieves better final performance, but it is very hard to find the right hyperparameters. Pre-normalization, on the other hand, offers better training stability because it is less sensitive to hyperparameter choices. So even if you don't search for the optimal hyperparameters, you can get good results with this approach. Pre-normalization shines where the number of layers is big. Let's do the benchmarking. We are going to consider pre-normalization as the baseline, and we are going to compare it to post-normalization. Here are the results. As you can see, post-normalization performed better than pre-normalization. In this case, I have a small model. I don't have a lot of layers. This is why post-normalization performed the best. But I'm just giving you the methods that exist and ways to implement them. And then it depends on your case. You might get different results if you have a bigger model or if you are training on a different data set. Now let's go to VS Code to see how to implement post-normalization. In the model script, here are the layer norms. And as you can see here, we are using pre-normalization. Why? Because we are applying normalization before the attention layer. So the output from the normalization layer is considered as the input for the attention layer. So post-normalization will basically change the order at which these operations are performed. So let me show you how this looks like. I have created this script that will basically change the order of operations. Okay, so inside the block class, or before I explain, let me put the scripts here on the right, and let me decrease the font size so that we can see both methods. Here on the right, you can see that here I added a comment. So just to mention that here we are using post-normalization. Here we feed the input to the attention layer, and after that we apply normalization. We do the same here for the feed-forward network. So we give this input to the feed-forward layer, and after that, after getting this output, we are going to add it to this input. This gives us X, and after that we apply normalization. You see, the difference is small, but it worked in our case. Now let's go back to the slides because we have one last thing to talk about, which is dropout. Dropout is useful when you want to avoid overfitting. Here is a diagram that explains dropout. On the left, we have the standard neural network. You can see that every neuron is connected to the other neurons that it can connect to. On the right, we have the network after applying dropout. You can see that some neurons are deactivated, which means that some connections are being dropped. This is what dropout does to your neural network. And if you want to read more about this, I have made sure to link to the original paper that introduced this idea. You should use dropout if training on a small dataset for a few epochs, because when you start to iterate over the data multiple times, this might lead to overfitting. But if you train on your dataset just once, then you will not have overfitting. LLMs train for one epoch because the dataset size is enormous. In this case, dropout is not needed because the model will not iterate over the data more than once. In this final benchmark, I am going to compare using dropout to not using dropout. Here are the results. And as you can see, because I have trained the model on just one epoch, not using dropout performed better than using dropout. Now let's go to VS Code in order to show you how to implement this, or what are the things that you need to change. So now let me search for dropout. You can see that we have defined dropout in many places. Here inside the head class, inside the multi-head attention class, and in the feedforward class. So if you don't want to use dropout, basically remove these lines. Whenever you find nn.dropout, remove it. Or in this case, we have stored it in this variable, so you can remove this and remove it whenever it is used. After you do that, use this new script inside the notebook, train your model, and maybe this will help you get better results. We arrived at the end of this video. I hope that it was useful and informative for you. In the next video, we are going to compare the original transformer model with a model that uses the best methods. So we are going to use, for example, for positional encoding, the rotary positional encoding. For attention, we are going to use maybe multi-latent attention or grouped query attention. We are going to remove dropout. We are going to use post-normalization, etc. So we are going to assemble these best methods that we found during these previous videos. The goal is to compare again the original model with the best model that uses the best methods. And the goal is to see that the loss curve keeps decreasing. For example, we are going to use ROPE, the rotary positional embedding. We should see that the loss decreases. After that, we are going to add to it multi-head latent attention. This should decrease the loss again. And we will keep going like this until we implement everything. At the end, we will see if by implementing these methods, we will get a huge boost in performance. See you in the next video. Hi everyone! In this video, we are going to use everything we have learned from the past videos. We will put it all together to update the 2017 transformer architecture in order to use the best ideas. We will go step by step. This way you can see how each small change makes things better. At the end, we will look at the old 2017 transformer architecture and compare it to the new one we built in this video. Like I said, we are going to build the best model using what we know now. We will make the model better bit by bit with small improvements. This picture shows the parts of the 2017 transformer architecture. First, I will change the multi-head attention part to multi-head latent attention. Then I will use rotary positional encoding to encode the positions. After that, instead of doing pre-normalization, I will use post-normalization. In the feed-forward network, which I called dense layer, I will replace the ReLU activation function with swiglu. And last, I will remove dropout. So you can see we have 5 steps. By the end, we should see a big improvement in performance. After each step, we will show a graph of the loss curves so we can see our progress. Let's begin with step 0. This is just the basic 2017 transformer architecture. It uses learnable positional encoding, multi-head attention, ReLU as the activation function, pre-normalization, layer norm, and dropout. In step 1, we change multi-head attention with multi-head latent attention. Here are the loss graphs for both steps. As you can see, the loss went down from 4.84 to 4.66. That's a drop of 3.72%. This is a good start. Now, in step 2, we use rotary positional encoding instead of the learnable positional encoding. This makes the loss go down even more to about 4.42. Now the total drop is 8.57%. This really shows how good rotary positional encoding is. Step 3 is about changing from pre-normalization to post-normalization. This brings the loss down by 9.27% in total. In step 4, we swap ReLU with SWIGLU. This change makes the total loss reduction even bigger. Now it is 10.72%. Finally, in step 5, we remove dropout. This brings our total loss reduction to 11.44%. Now, let's clear the graph and just show step 0 and the very last step. Here is the graph. As you can see, there is a big difference between the two loss curves. I am really happy to see this. It shows that all our hard work trying to find the best methods for each part paid off. The loss in step 0 or phase 0 was around 4.84, and in the last step it went down to 4.28. Now let's go to VS Code in order to show you the scripts that I have created. I have opened the project in VS Code, and if you open the transformer folder, you should see that I have added 4 scripts. Even though in the slides I have mentioned that we have 5 phases, here I have only 4 because multi-latent attention, we have already done that before, and yeah, we have it here, so there is no need to recreate it. What you see here is basically just me merging the old scripts that we have into this final phases. And I have also created notebooks that use these scripts. If you open the notebooks folder, you will see that we have them here. It's these 4, 951, 952 to 954. And as you can see, they use the 4 phases that we have here. If you have made it to the end of this video, I want to say thank you for watching this course. This is the end of this video. I really hope you have learned a lot and enjoyed this journey with me. We have one more video left. In that video, I will wrap things up and give a quick summary of what we covered in this course. See you next time. We have reached the end of the course. Congratulations! You have done an awesome job. Let's quickly go over what we have learned. We started our journey by looking at the original transformer from 2017. Thanks to that architecture, we were able to create our first language model. This course was all about exploring the improvements and new ideas that were proposed from 2017 to 2025 that helped make the transformer even better. As you can see from this diagram, we have tried a lot of ideas and we had to learn a lot in order to get here where we have improved the transformer architecture drastically. We observed that these new ideas significantly enhanced the transformer architecture across various aspects, such as memory usage, inference speed, better results, and more. We also noticed that each improvement helped lower the model's loss, which means it got better at understanding and predicting. We have seen this in the previous video when we applied just MLA. That helped reduce the loss a bit. When we added to it really Swiglu, no dropout, etc., we kept reducing the loss further. And here is the takeaway. Transformers are still changing and getting better. If you want to stay on top of things, keep an eye on the latest research. Thanks a lot for watching the course.